In 1972, French geologist Michel Siffre locked himself away for 6 months inside a cave in Texas. The mission, funded by NASA, was designed to mimic the conditions of future space voyages where astronauts might face extreme isolation and lose all natural cues about time. Deep underground, Siffre had everything he needed to survive: food, water, and scientific equipment to track his sleep cycles. But one thing he didn't have was a clock. No watch, no sunrise, no sunset. He could only switch the lights on and off at will, drifting through life without structure. And it didn't go smoothly. The human mind is not built for timeless voids. Siffre began to suffer from depression, memory lapses, and, at times, even suicidal thoughts. But the most fascinating part was how his perception of time collapsed. At first, his days naturally stretched to 25 or 26 hours. Then, things spiraled. His waking periods grew longer and longer, sometimes 32 hours followed by 16-hour nights. In effect, his body created 48-hour days, double the normal length. By the time researchers ended the experiment on day 179, Siffre was convinced he had only been underground for 151 days. He had lost nearly a month to his distorted inner clock. What's strange is that this wasn't the blissful time loss of being on vacation. It was the erosion of time while he was battling despair and isolation. And Siffre's case wasn't unique. Other cave experiments revealed even more dramatic distortions. In 1988, Véronique Leguin spent 111 days underground in France, but swore it had only been 42. A year later, Italian interior designer Stefania Follini survived 4 months in darkness, yet believed she had spent just 2. In 1993, an Italian sociologist took isolation to the extreme. He spent an entire year inside a cave. When he finally resurfaced, he was convinced it was still summer. In reality, winter had already arrived. Stories like these reveal something profound. Our perception of time is not objective. It's a construct of the brain. In fact, you could argue that subjective time is no more real than color. There are no colors out there in nature, only electromagnetic waves. The brain paints those waves into reds, blues, and greens. It's the same with time. Like letters of the alphabet that we attach sounds to, our experience of time is a mapping, not the thing itself. And because it's generated in the brain, it's vulnerable to illusion and distortion. With color, at least, we know what the brain is interpreting: electromagnetic wavelengths. But when it comes to the flow of time, what is the real, physical phenomenon that the brain is translating? If you think the answer is obvious, think again. Science itself admits that the question is still a mystery. What you're experiencing right now, the sensation of the present moment, is one of the deepest unsolved problems in science, and the difficulties don't end there. Even defining objective time turns out to be nearly impossible. Over 1,500 years ago, Augustine of Hippo wrote, "If no one asks me, I know what time is. But if I try to explain it, I do not." Centuries later, physicist Richard Feynman echoed the same frustration. It would be nice if we could come to terms with the fact that time is one of those things we probably can't define. It's not the definition that matters, but how we measure it. In the strictest sense, time is nothing more than what a clock measures. And yet, most of us feel that time is a continuous flow, a river of events passing from past to future through the fleeting present. The past is gone. The future doesn't exist yet. Only the now is real. That's our intuition, but modern physics shows us that this intuition is deeply misleading. The real nature of time doesn't resemble our everyday experience at all. And to see how far off we are, consider a simple thought experiment. Imagine a bizarre train. It's only 1 car long, but that car stretches 400,000 kilometers, about the distance from Earth to the Moon. The train rushes forward at 200,000 kilometers per second, 2/3 the speed of light. In the exact middle of this train stands a man holding 2 pistols, one pointed toward the front window, the other toward the back. Each pistol fires bullets at 200,000 kilometers per second. He pulls the triggers, and from his perspective, the bullets shatter both windows exactly 1 second later, perfectly simultaneous. Seems obvious, right? But from the viewpoint of someone standing still on the platform, the story changes. The backward shot, relative to the train, moves at 200,000 kilometers per second. Relative to the platform, it's effectively motionless, so it hits the rear window right on time. But the forward shot is different. Relative to the train, it also moves at 200,000 kilometers per second. Relative to the platform, you'd expect 400,000 kilometers per second. Yet, that speed is impossible. It exceeds the speed of light. Special relativity steps in. From the platform's perspective, the bullet is slowed to about 277,000 kilometers per second, which means it takes longer to reach the front window. So, the two windows don't break at the same time. The back shatters first, the front later. And this isn't an optical illusion. It's a measurable, physical reality. Relativity has been confirmed in countless experiments, all pointing to the same conclusion. Simultaneity is relative, not absolute. This phenomenon is known as the relativity of simultaneity, and it reveals something almost incomprehensible about the universe we inhabit. Imagine it. In one version of reality, both windows of the train are either intact or shattered at the same instant. In another, there's a moment when the back window is already broken, while the front one remains untouched. And here's the unsettling part. These aren't two parallel universes. They happen in the same universe. Two observers watching the same event genuinely disagree about what's real. So, whose version is correct? According to special relativity, both are equally real, equally valid. Logic tells us two contradictory statements can't both be true, but physics tells us otherwise. The universe isn't obliged to obey our human rules of logic. Now, most popular explanations stop here, leaving us with this paradox and moving on. But let's not. Let's ask the harder question. What kind of universe allows this? What kind of reality makes contradictions real? Physicists and philosophers have wrestled with this question for over a century, and their answers have led to a model of reality that looks nothing like our everyday intuition. Yet, it's the model that science keeps pointing us toward. And here's the disturbing part. It's not a comforting picture. Our brains, the most complex mechanism we know of, didn't evolve to understand time as it really is. In fact, the brain's very structure might be marked by the same contradictions that shape the cosmos itself. This brings us to Dean Buonomano, an American neuroscientist and author of Your Brain is a Time Machine. Buonomano was one of the first to dedicate much of his career to exploring how the human brain encodes time. While writing his book, he drew not only on neuroscience, but also on insights from physicists and philosophers. And his conclusion is sobering. What feels so familiar, our sense of time's passage, may be nothing more than an illusion. Einstein himself once joked, "When you sit with a pretty girl for 2 hours, it feels like a minute. But when you sit on a hot stove for a minute, it feels like 2 hours." That's relativity. The humor is charming, but behind the joke lies a deeper, unsettling truth. Before we dive into the strange physics of time, let's ground ourselves in what time actually means to us as humans. On one level, this helps us appreciate the sheer madness of the second half of the story. On another, it makes us realize that maybe it isn't so crazy after all. First, let's be clear. Those bizarre distortions of time people experienced in caves were the result of highly unnatural conditions. In everyday life, our bodies rely on something much more reliable, an internal clock. You already know you have one. You can guess when a traffic light is about to turn green or how long a commercial break will last. But have you ever thought about where this clock is or what it actually looks like? According to neuroscientist Dean Buonomano, timing is so crucial that it isn't managed by a single clock in the brain. Instead, timekeeping is woven into the brain's very operating system, into neurons, synapses, and networks themselves. In other words, nearly every circuit in your brain participates in measuring time. Buonomano puts it simply. If you wanted to describe the essence of brain function in a single phrase, the best definition would be predicting the future. Seen this way, the brain is a kind of time machine, not one that travels through centuries, but one that constantly works with time, moment by moment. For hundreds of millions of years, evolution has been a competition in prediction. Predators that anticipated the movements of prey survived. Prey that anticipated the movements of predators survived. And both tried to anticipate the behavior of potential mates. Life itself is built on forecasting. Animals store food, build nests, and prepare for the changing seasons. Fail to anticipate tomorrow, and you won't live long enough to pass on your genes. Whether you realize it or not, at every instant, your brain is silently making predictions about what's about to happen next. And these predictions, usually just a few seconds into the future, happen unconsciously. If a rubber ball rolls off a table, your hand moves to where it will bounce. If a slice of pie falls, you respond differently because you know exactly how it will land. Animals do the same. Bring a cat into a new home, and it will anxiously sniff every corner, building a mental map of the space to prepare for the next minutes and hours. A wolf pauses to catch scents and sounds, scanning for prey, rivals, or mates. A dog leaps into the air for a frisbee because it can calculate where that spinning disc will be in a second. Even birds measure time. As pollinators, they can track how long it's been since they last visited a flower, returning only once nectar has had time to refill. In fact, nearly everything in human life, from hurling a spear at moving prey, to laughing at the perfect punchline, to playing Beethoven's Moonlight Sonata, or even regulating our daily sleep-wake rhythms, depends on our ability to measure and predict time. The brain doesn't just tick off seconds, hours, and days like a stopwatch. It creates temporal patterns, musical rhythms, dance sequences, and the precise coordination of movements that let gymnasts flip through the air. Our instinct to clap, snap, or nod along to music is proof that the brain is constantly predicting the future. It looks seconds or even fractions of a second ahead, anticipates the next beat, and aligns our actions with it. Want proof? Try snapping your fingers deliberately offbeat to a song. Suddenly, you'll find it takes effort and concentration, but staying on the rhythm feels almost effortless. That's your brain's predictive machinery at work. Humans may be unique, or at least rare among Earth's creatures, in our ability to mentally travel through time. Sometimes we even abuse this gift, replaying the past or worrying about futures that may never come. But most importantly, the brain creates our sense of time, our feeling of living inside it. You can test this for yourself. Ask someone to look from your left eye to your right eye. You'll notice their eyes moving. It takes a fraction of a second. Now, try it in the mirror. As you shift your gaze from one eye to the other, your reflection doesn't seem to move at all. Why? Because the brain deletes those moments. It also erases the split seconds when you blink. It may seem trivial, but it adds up. At highway speeds, during the time it takes to blink, a car travels about 5 meters that simply vanish from your awareness. On average, the brain cuts out nearly an hour of raw material from our daily experience. Formula One drivers, racing at over 350 kilometers per hour, are even trained to control when they blink on the track. So, what feels like a seamless, continuous reality is, in fact, a carefully edited construction by the brain. And yet, all we truly experience directly is the present moment. The past is memory. The future is prediction. Only now feels real. But what is now? Try to hold on to it, and it slips away instantly. For most of us, the present flows. But for one man, it froze nearly 40 years ago. That man is Clive Wearing, a British musicologist. After a viral brain infection damaged his hippocampus, Clive lost the ability to form lasting memories. His world lasts only 7 to 30 seconds at a time. He lives in an endless cycle of waking up, rebooting consciousness, and forgetting. Imagine opening your eyes every 20 seconds, convinced you've just awakened from a coma again and again for decades. That is Clive's reality. He was advised to keep a journal. The entries are haunting. 8:31 a.m. Now I am truly awake for the first time. Crossed out. 9:06 a.m. Now I am completely, utterly awake. Crossed out again. 9:34 a.m. Now I am truly, truly awake. As his pages continue, the handwriting grows larger, more desperate. I am awake. I am alive. As if by writing, he could pin himself to the train of time, stop it from leaving without him. But each time, he failed, because when he looked back, he couldn't remember writing the earlier lines. Asked in a 2005 documentary what his condition felt like, he replied, "You are the first people I've seen. There's no difference between day and night. No thoughts, no dreams. Day and night are the same, empty, just like death." And when asked if it was difficult, he said, "No, it's exactly like being dead. And being dead is easy. You do nothing at all." It was the same. Exactly. This tragic story doesn't prove anything scientifically, but it suggests something profound. Perhaps what we call the present moment depends on short-term memory. Without memory, the now collapses into fragments, and life becomes a series of endless awakenings. Our experience of time doesn't arrive in one seamless stream. It comes in pulses, in bursts of awareness, each lasting a certain span. Consciousness, in this sense, is less like a still photograph and more like a sustained musical note. As neuropsychologist and Harvard professor Steven Pinker once observed, matter is distributed in space, but consciousness exists in time. And this is as obvious as the fact that I think implies I exist. That raises a deep question. How finely divided is consciousness in time? How short can a moment truly be? Now, a quick disclaimer. What I'm about to mention involves substances that may be illegal where you live, and I am not encouraging their use. But it's worth noting that psychoactive drugs can profoundly alter our perception of time. William James, one of the founders of modern psychology, once wrote about his own experiences. In hashish intoxication, a curious sensation of time dilation occurs. We begin to speak a sentence, but by the time we reach the end, it feels as if we began an eternity ago. Modern experiments confirm this. The active compound in cannabis, THC, has been shown to distort time perception. In one early study, subjects were asked to signal when they thought a minute had passed. Under normal conditions, they were accurate. But after ingesting THC, many believed a full minute had gone by after just 42 seconds. But altered states aren't the only way humans encounter time distortion. Many of us have heard stories, or even experienced it ourselves, of time slowing down during moments of danger, emotional stress, or near-death situations. Why does this happen? Dean Buonomano outlines 3 possible explanations. The first is brain overclocking. Just as a computer processor can be temporarily pushed to higher speeds, the brain may, in moments of crisis, boost its processing power by 10 to 20%, sharpening perception. The second is the hypermemory hypothesis. According to this idea, we don't actually perceive events in slow motion while they're happening. Instead, the brain encodes the memories with unusually high detail, greater temporal and spatial resolution. Later, when we recall those memories, the richness of the detail makes the event feel as though it unfolded in slow motion. But there's a problem. If slow motion is only a trick of memory, it doesn't explain why people often react faster, more precisely, or even save their lives in those moments. Nor does it account for the widespread belief that time really feels different in the middle of danger. Buonomano himself describes a car accident he survived. His vehicle was struck, flipped over, and slammed into a telephone pole. He recalls, "It all happened very slowly. In that moment, I even thought to myself, wow, time really is slowing down." And yet, he admits he didn't react with superhuman speed. He doesn't even remember the airbags deploying. If his perception was already altered during the crash, then hypermemory alone cannot explain the effect. Which brings us to the third and most intriguing hypothesis, what Buonomano calls the meta-illusion. To get a sense of this, try something odd right now. Place your hand on a nearby object, a wall, a table, a phone, and pay close attention. Doesn't it seem strange that although the formation of the sensation of an object occurs in the brain, we don't feel it in our head? This sensation is literally transferred to a specific point in space. Buonomano writes that one of our deepest and most convincing sensations is the feeling that our bodies belong to us, our arms, legs, fingers. But, he argues, this too is an illusion. You may have heard of phantom limb syndrome. After an amputation, many people continue to feel the missing arm or leg as vividly as if it were still attached. The brain is so committed to maintaining the illusion of body ownership that it continues projecting it even after the limb is gone. This leads to a radical conclusion. It's not the phantom limb that's an illusion. It's the feeling of ownership itself, even of the limbs we still have. The brain is remarkably flexible in creating these sensory mirages. Take the rubber hand illusion. If you place a fake hand in front of you and your real hand is hidden, the brain can be tricked into accepting the rubber one as your own. You'll feel touches on the artificial hand as though they were happening to you. The brain literally relocates the sense of self into an object that isn't part of your body. From here, Buonomano takes a daring step. If the brain can fabricate illusions of space so easily, why shouldn't it also fabricate illusions of time? This is where his idea of the meta-illusion comes in. The flow of time itself may be nothing more than a construction of the brain, an illusion of an illusion. Think of YouTube's playback settings. You can speed up a video to 2x or slow it down to 0.5x, and your brain still makes sense of it. After watching at double speed for a few minutes, normal playback suddenly feels slow. Given enough exposure, your brain would adapt, and the accelerated world would feel perfectly natural. In the same way, our perception of time isn't fixed. It stretches and compresses constantly. The brain can even simulate actions faster than reality allows. You can think a phrase much faster than you can speak it aloud. You can mentally tie your shoes or rehearse a movement in seconds, far quicker than your body could ever perform it. Real-world experiences confirm this elasticity. Take the words of a 24-year-old race car driver whose car flipped at 250 kilometers per hour, soaring 10 meters into the air. It seemed to last forever. Everything unfolded so slowly. I felt like I was on stage, watching myself flip again and again in the car like I was both the actor and the audience. A 21-year-old university student, after a serious crash, recalled, At that moment, time seemed to stand still. It lasted forever. Even space felt wrong, as if I were watching a movie in a theater. And a World War II soldier whose vehicle struck a mine described the same phenomenon. I didn't feel like time was passing at all. Nothing was changing. Space itself seemed distorted. I felt like I existed only in my thoughts. These testimonies point to something extraordinary. In moments of extreme stress, the brain may bend not only memory, but the very fabric of lived time itself. In critical moments, not only our perception of time, but also of space begins to warp. Many people describe the sensation of floating outside their own bodies, watching events unfold as if from the outside. Buonomano notes, in any other context, such reports would be labeled hallucinations or disturbances of consciousness. Perhaps during fight or flight responses, the brain is flooded with neuroactive chemicals, overloading its circuits and producing these distortions. If that's the case, then the time dilation effect is best understood as another kind of altered consciousness, not a faithful reflection of reality. But he also emphasizes that the three hypotheses, brain overclocking, hypermemory, and meta-illusion, aren't mutually exclusive. Time perception is strange and slippery. We all distort it, even in everyday life. Waiting in line or for a phone call can feel twice as long as it actually is. On the other hand, with music playing, waiting feels shorter. Companies know this. That's why you always hear music while on hold. So yes, to some degree, we can slow down or speed up our personal time. But what happens when we stop talking about perception and instead ask, what is time as a physical process? If we keep dividing time into smaller and smaller slices, hours, seconds, milliseconds, nanoseconds, will we eventually hit a fundamental unit of time that cannot be divided further? Some physicists call this theoretical, indivisible instant, a chronon. Clocks are humanity's most precise inventions, and we've become almost obsessed with telling time. In the past, even neighboring town clocks rarely agreed. But Einstein's theory of relativity showed us that no clock can be absolute. Gravity itself affects the rate at which time passes. An atomic clock on a satellite ticks faster than one on Earth. More astonishing still, even two identical atomic clocks placed at different heights, one on the floor, the other on a table, will eventually disagree. Time itself changes with location. Richard Feynman once remarked that because of gravitational time dilation, the Earth's core should be younger than its crust by a few days. Later refinements showed he had underestimated. In fact, over the lifetime of the planet, the core is about 2.5 years younger than the surface, which means, in a very real sense, the center of Earth is still back in 2022, while we live in 2025. We now measure time with a precision unmatched by any other parameter in science. In fact, we use time itself to define other quantities. A meter is literally the distance that light travels in a fraction of a second. Our progress in measuring time is astonishing. And yet, science still cannot answer the most basic question. Is time continuous, or is it made of discrete moments? If time were made of indivisible instants, paradoxes arise. Consider Zeno's famous dichotomy paradox. To travel any distance, you must first go halfway. But to reach halfway, you must cover half of that, and so on, infinitely. If each step requires a distinct moment to exist, then motion could never begin. This is the mystery of time, a mystery we are only beginning to glimpse, and here is where things turn uncomfortable. As Einstein once said, for us physicists, the distinction between past, present, and future is only a stubbornly persistent illusion. You've probably heard before that the laws of physics are symmetric with respect to time. They don't recognize a preferred direction. They don't privilege the present. To the equations, past, present, and future are all equally real. In this view, the now is no different on the timeline than here is in space. And that's why many physicists and philosophers accept a radical idea. Every moment in time, past, present, and future exists equally. And once again, the main reason we are forced to take this idea seriously is relativity itself. Remember the train thought experiment we discussed earlier. Each observer has their own present, shaped by their motion and perspective. What is simultaneous for one person may not be for another. The relativity effect we saw with the train is fascinating, but let's be honest, it feels far removed from everyday life. After all, we don't see kilometer-long trains flying at near light speed. So why should we care? How does this strange physics touch our reality? To answer that, let's go further. In his book, The Emperor's New Mind, Nobel Prize-winning physicist Roger Penrose introduces a thought experiment that forces us to rethink reality itself. Even at very low relative speeds, relativity predicts enormous differences in chronology if the distances involved are vast enough. Two people slowly passing each other on the street here on Earth see the same events around them. But imagine that at the exact moment they pass, they are both transported to the Andromeda galaxy, 2.5 million light-years away. Suddenly, their present moments no longer line up. For one, the Andromedan fleet may have already launched on a mission to destroy Earth. For the other, the decision to launch hasn't yet been made. As Penrose puts it, while for one passerby, the fleet is already in flight, for the other, the decision has not yet been taken. This isn't science fiction. Special relativity has been confirmed with extraordinary precision. The caveat, of course, is that neither pedestrian could ever see what's happening in Andromeda. Light and any information takes 2.5 million years to cross the void. The point isn't about observation, it's about reality itself. If we could freeze-frame the entire universe from each pedestrian's perspective, their snapshots would look nearly identical where they cross paths, but diverge more and more the farther we move away into space. And this doesn't just apply to conscious observers. Any material point, whether a rock, a particle, or a passing human, carries its own accounting system of simultaneity. Each has its own present moment, which may not align with anyone else's. Here lies the paradox. Two people standing in the same place at the same instant can still inhabit different versions of now, yet they remain in the same universe. If one turns around and follows the other, their perspectives sync back up, though never perfectly. The difference isn't that they live in separate universes, but that relativity makes simultaneity itself relative. From the perspective of aliens in Andromeda, the same applies to us. Some of them would see you as existing in yesterday, others would see you in tomorrow. So, again, what does a universe like this look like? Special relativity tells us that through every point in spacetime passes an infinite number of possible planes of simultaneity. Each one slices reality differently, defining a different set of events as the present. Even the tiniest motion of your head shifts your plane of simultaneity and thus changes your personal now. In fact, your head, your arms, your legs, even different parts of your body, all technically occupy different slices of present at once. It sounds absurd, but if we could step outside the universe, fly beyond its boundaries, and turn back, we would see something astonishing. Reality would appear as a static four-dimensional block, with time as just another dimension, like space. Within this model, speaking of now is no different from speaking of here. Every moment exists. Every moment is real. Scientist and mathematician Rudi Rucker, who also happens to be the great-great-grandson of Hegel, once wrote, "As it turns out, it is actually impossible to find any objective and universally acceptable definition of all space taken at a given moment." This follows directly from Einstein's special theory of relativity. Thus, the idea of a block universe is not just an attractive metaphysical theory. It is a well-established scientific fact. Interestingly, when Einstein first published his paper on special relativity, he did not claim that time should be considered the fourth dimension of a block universe. That leap was made by his former professor in Zurich, Hermann Minkowski, the same professor who once dismissed Einstein as a lazy dog. In 1908, Minkowski recast relativity in a new geometric form. His words were as bold as they were prophetic. "The views on space and time that I wish to convey to you arose from experimental physics, and therein lies their strength. They are radical. From now on, space itself and time itself are doomed to disappear, and only a kind of union of the two will preserve an independent reality." Of course, we cannot picture a true four-dimensional block, but to illustrate it, physicists often drop one spatial dimension, leaving us with a 3D diagram. In this representation, the concept of a plane of simultaneity becomes easier to grasp. Now, imagine a more extreme scenario. Take a human here on Earth and an alien from a galaxy not just millions, but 10 billion light-years away. If they are at rest relative to each other, their clocks stay in sync. Their present moments lie on the same slice of spacetime. But if the alien starts moving even at a modest speed, their plane of simultaneity tilts. And because moving clocks tick more slowly, that tilt points toward Earth's past. At such a vast distance, even a tiny tilt results in a colossal shift in time. From the alien's perspective, Earth's present moment might fall somewhere in the 19th century. And relativity tells us this moment is just as real as the one you inhabit right now. By adjusting the alien's speed, direction, and distance, one could shift Earth's present to almost any era, the year 1000 or the year 3000. This is one of the reasons physicists doubt the feasibility of faster-than-light travel. It wouldn't just move you through space, it would fling you through time. Howard Phillips Lovecraft once wrote, "The wave suggested to him that any shape in space is formed by the intersection of some multi-dimensional figure. A square is the result of a section of a cube, and a circle the section of a sphere. Three-dimensional cubes and spheres arise from the intersection of four-dimensional figures, things humans had only guessed at until now, and occasionally dreamed about. If you once thought of time as a flowing river, physics now suggests it is more like a frozen block. And common sense rebels at the thought. Why? Because if we truly live in a block universe where past and future are fixed and unchanging, then our cherished sense of free will collapses. Every decision you believe you are about to make has already been made. Of course, a block universe might sound like destiny carved in stone, but does that mean life is predetermined? Not necessarily. What's fascinating is that humans seem to process time using the very same mechanisms we use to understand space. At the most fundamental level, the brain may not even distinguish between the two. This brings us to Swiss psychologist Jean Piaget, who revolutionized developmental psychology. He explored how children grasp abstract concepts like number, space, and time. Piaget believed there was a deep link between a child's intuitive sense of time and Einstein's relativity. In one experiment, children were shown two snakes moving side by side. They started and stopped at the same time, but one slithered farther because it moved faster. Children aged 5 to 6 insisted the longer-moving snake must have stopped later. In other words, they intuitively connected distance with time, as if they sensed, however crudely, that faster movement stretches time. Piaget's ideas impressed even Einstein, who remarked that they were so simple, only a genius could have thought of them. But what about adults? The same strange blending of space and time shows up in us, too. Take two light bulbs flashing alternately, always 8 seconds apart. When researchers varied the distance between them 20, 40, or 80 centimeters, people judged the intervals differently. The farther apart the bulbs, the longer the gap felt, even though it was always 8 seconds. This is called the Kappa effect. The conclusion? Our brains intertwine space and time at the deepest level. We can't help but imagine chronology in spatial terms. Think about how you picture the years 2021, 2022, and 2023. Most likely, you line them up left to right in your mind. That feels natural, but it isn't universal logic. It's a neural habit. If time can be mapped in space, why not right to left, or even bottom to top? After all, wouldn't moving upward better match our intuition of progress? Yet almost everywhere, people imagine time flowing left to right. Experiments confirm this. In one task, participants had to judge the length of musical notes. They performed better when using their left hand to mark short intervals and their right hand for long ones. Reverse the setup and their accuracy dropped. As Buonomano put it, it's as if, in the neural circuits, the mental timeline runs from left to right. More evidence comes from research by cognitive scientist Lera Boroditsky. Patients with strokes that damage the right parietal cortex often develop left-side neglect. They may eat only the right half of their meal or wash only the right side of their face. Boroditsky's lab found that such patients also struggle to place memories on a timeline. Their mental maps of past and future become scrambled. And if you listen closely to how we speak, you'll notice that our language constantly borrows from space to describe time. We look ahead to the future, back at the past. Winters are coming. Life is short. Time is long. Virtually every language on Earth does this. Rarely does it work the other way, except for phrases like, "I live half an hour from here." As Buonomano writes, overall, we still don't fully understand how neurons in the hippocampus or anywhere else encode the magnitude of spatial and temporal parameters. But from philological, psychophysical, and neurophysiological evidence, it seems clear. Space and time are fundamentally intertwined in our neural circuits. One might argue that time can't truly be treated as a spatial coordinate. After all, space and time seem fundamentally different. Move through space, and you see geometry change. Objects grow larger as you approach, smaller as you retreat. Nothing like that seems to happen as we move through time. But that's not quite true. With every movement through space, something unexpected does happen. Objects shrink along your direction of travel. This is known as Lorentz length contraction. At everyday speeds, the effect is almost imperceptible. Driving at 60 kilometers per hour, a parked car in front of you actually shortens by about 8 quadrillionths of a meter from your perspective. Insignificant, but real. Push this to extremes, and the results are mind-bending. Imagine the Saturn V rocket, the 110-meter giant that carried astronauts to the moon, accelerating to just 1 meter per second below the speed of light. To those astronauts, the moon's diameter, normally 3,474 kilometers, would shrink along their line of motion to a mere 284 meters. That's relativity in action. In fact, MIT even created a first-person 3D game in 2012 to simulate what the world would look like if the speed of light were as slow as walking speed. The game accounts for all the bizarre distortions predicted by relativity. The slower you move through time, the more the geometry of space twists around you. So even here, time behaves with distinctly spatial properties. And yet, when we try to unite the physics of time with our inner experience of it, we hit a wall. This is one of the universe's deepest mysteries. As physicist John Wheeler once wrote, "Of all obstacles to a deep understanding of nature, none is as formidable as time. To explain time, you must explain existence. To explain existence, you must explain time. To uncover the hidden link between them is a task for the future." In space, we can move in any direction forward, backward, left, right, up, down. But in time, we move only one way, always forward, never back. At least, that's how it feels to human consciousness. We may bend the rate of time's passage, slowing it down with motion or gravity, distorting it with stress or memory, but we never reverse it. Yet here lies the paradox. The fundamental laws of physics say nothing about time's direction. Newton's equations, Maxwell's laws of electromagnetism, Einstein's relativity, even Schrödinger's equation in quantum mechanics all work equally well, whether time flows forward or backward. None privilege the present moment. This leaves us with a disturbing contradiction. Physics compels us toward the block universe, a timeless structure where all moments exist equally. Yet our lived experience insists the present is unique, that time passes. Even Einstein struggled with this gap. The philosopher Rudolf Carnap recalled a conversation with him. Einstein once admitted that the experience of the present troubled him deeply. For humans, the present feels special, fundamentally different from past and future. But physics cannot account for this distinction. The fact that science could not explain it seemed to him a painful but inevitable retreat. Roger Penrose echoes this discomfort. Reflecting on his famous Andromeda paradox, he noted, "According to special relativity, the concept of now simply does not exist. At best, we can speak of an observer's space of simultaneous events, but that is not the same thing. An analogy often comes to mind. The universe, with all its events, is like a vinyl record. Our consciousness is the needle, tracing the grooves from past to future. But even this picture collapses on closer inspection. Consciousness is not something outside the universe, it's part of it. In that case, the needle must itself be carved into the record. This is the heart of the problem. The block universe of physics seems undeniable, yet our lived experience insists on the passage of time. How can the two ever be reconciled? Many physicists and philosophers believe they cannot, and that the only resolution is to accept the flow of time as an illusion. But what does that mean? How can something as vivid as time be illusory? As theoretical physicist Paul Davies puts it, "In my opinion, the biggest problem lies in the glaring discrepancy between physical time and subjective, psychological time. The apparent sense of movement, or passage of time, perhaps acquired through a backdoor of thought, is a profound mystery. Is it related to quantum processes in the brain? Does it reflect an objective property of time in our material world that we cannot yet detect? Or will the flow of time turn out to be purely a mental construct, an illusion, or a conscious error?" Think about vision. What we see is a mental construct. Colors don't exist in the outside world. There are only electromagnetic waves of different wavelengths. Blue is our brain's interpretation of radiation at about 470 nanometers. Smells don't exist out there either. What exists are molecules, say, sulfur compounds, which the brain interprets as the stench of decay. These illusions are adaptive because they correspond reliably to real physical features of the world. They guide survival, but time is different. Where is its physical equivalent? What does the flow of time correlate with? Physics tells us nothing, which suggests our sense of time is not just an illusion like color. It may be an illusion in the most literal sense, something conjured within us that has no counterpart outside. Philosopher Craig Callender puts it bluntly: the equations of physics don't tell us what's happening right now. They're like a map without a circle saying, you are here. There is no present moment in time, and therefore no passage of time. Reconciling this, the inner human experience of time, with the external laws of nature is one of the hardest open problems in science. It sits at the crossroads of physics, neuroscience, psychology, and philosophy. As physicist Brian Greene admits, is science unable to grasp a fundamental property of time that the human mind perceives as naturally as lungs absorb air? Or does the mind simply project onto time some quality of its own making, absent from the laws of physics? If you ask me, during working hours, I'd lean toward the latter. But at night, when critical thought drifts into the rhythms of daily life, it's hard to resist the former. At the beginning of this video, we saw how the very structure of the universe seems to have shaped the architecture of the human brain. And, as we noted in the analogy with relativity, the brain has a remarkable tendency to make time spatial. But Dean Buonomano challenges us to flip the perspective. He asks, aren't we biased toward one interpretation of physical law over another because the brain interprets time in a particular way? In other words, the brain and the laws of physics are not completely independent. It's not just that the brain obeys physical laws, it's also that our understanding of physics is filtered through the design of the brain itself. Put more simply, maybe the reason we see a block universe in the equations is because of how our spatially oriented brains read those equations. How impartial can our interpretations really be? Otherwise, once again, humanity risks being out of place in the very physical picture of the world it has created. And it's important to note, physics does not unambiguously prove that we live in a four-dimensional block universe. That interpretation is powerful, elegant, and widely accepted by many leading scientists. But it is still an interpretation. Physics still struggles to weave a fully coherent theory of time. And, as is always the case in science, there is no consensus. Even among those who embrace the block universe, attempts have been made to salvage the feeling of time's passage. David Deutsch, in The Fabric of Reality, writes, objectively, the present does not exist. We do not sense time flowing or passing. We sense differences between our present sensations and our present memories of past sensations. Brian Greene offers another analogy. Every moment in spacetime, every slice of time, is like a frame in a movie. Each slice is the present moment for you, filled with sensations, thoughts, and memories rich enough to create the impression of flow. But this sense of passage does not require that earlier frames be sequentially illuminated. But are these answers, or just clever ways to sidestep the problem? Perhaps the ongoing clash of ideas will eventually bring us closer to the truth about time, or perhaps the mystery is even deeper than we imagine. In his book Spooky Action at a Distance, also published as Non-Locality, science writer George Musser gathers arguments suggesting that space-time itself may not be fundamental, that it may emerge from something more profound. As philosopher of physics, Tim Maudlin writes, the world is not simply a collection of separately existing, localized objects, externally related only by space and time. Something deeper, more mysterious, binds the fabric of the universe together. We have only just reached the point in the development of physics where we can begin to speculate about what this might be. And maybe that's the final lesson. The more we learn about time, the more it slips through our fingers. Is it a dimension, a construct, an illusion, or the key to reality itself? For now, no one knows. Thank you all for watching.